Now, I realized that in a lot of my videos, I talk about light curves. I say we've used this light curve to maybe we found a exoplanet. We figured out that this star is pulsating, or some other various different things that we've discovered using a light curve. But I haven't really explained what one is. So I'm going to use this video to basically explain what a light curve is and how you acquire one. So firstly, astronomical objects, don't always stay the same brightness. Now we talk about how bright the object is, but the more technical terms we might refer to things like flux, the magnitude, things like that. But I'll just talk about brightness for this video so it makes sense. So you've got a star right in the center there, and that appears to be blinking, so it's going on and off. It's not really going on and off, it's just getting brighter and dimmer periodically. And if we were to basically take a measurement of that over time and calculate how bright it was, we would then acquire our light curve. So it's basically the brightness of an object over time, and we can see how it's varying. Now, lots of those other stars in there would have a flat light curve because they don't appear to be changing in brightness, although they might have slight variations. The obvious one is in the center. So, what do you do to actually acquire it? Well, we have the star that we want to measure. So I've pinpointed the one that is actually varying here. I've then noted some reference or standard stars. Now, this is just for the purpose of this video. These are not proper standard stars or reference stars. I'm just pointing out that you would use a number of stars to then calculate the brightness, magnitude, or flux of the star that you're actually measuring, because they would be stable. They are well understood stars. So they would be in a pretty standard catalogue. They've had various different measurements taken. They're fairly stable. You can use that as like a reference point to calculate your star that you're interested in. Ideally, you want to use stars that are of a similar sort of brightness. So you don't want ones that are a lot brighter or too dim, because when you take the image, some are going to be overexposed and then you get nonsense basically for your value. So you'd want stars that are of a similar brightness. Again, ones I've pointed out probably aren't, that are a little bit brighter. And you want ones nearby. Now, why do you want them nearby? Well, if you can do it in a single image, it makes life a lot easier. But if you go too far away, then you have to do additional adjustments for things like air mass. So you're looking through more of the atmosphere. So you've got to do corrections before you can even start to do this. And actually, it's not an easy process. It sounds straightforward that you take a measurement, you measure it to nearby stars. That's it. We can then calculate a brightness of this star. But there's a lot of calibration you've got to do in order to get to that point. So let's say you take a single image, you find a value for how bright that star is. You also have a time that you took that. So for a single image, you can plot that on a plot of the brightness of the star and then the time it was taken. So you just have a single point there. Now, what you would do to build up your light curve is you would keep taking images and you would calculate the magnitude or the brightness of that star at each one, and then you would put it on your plot again. And over time, you would build up something that might look a little bit like this, a bit of a scatter plot, essentially. Now, it would vary because you're looking through like the atmosphere. There's obviously distortion that you're fighting with, so you're never going to get an absolutely perfect trend line anyway, because there's going to be slight variations. I mean, even the temperature of your equipment is going to give you a slightly different value, so you're going to get some variation. Now, what you can do then is you could fit a trend line, or you can look at a best fit for that particular data set. Now, this example I've given you here, it has a upward trend, so in time it looks like the star is getting brighter. Now, that can tell you a lot of very interesting information about the star. So though we can't see the star physically, like the surface, what's going on, the actual environment that it's in, we can monitor how bright it is over time, and that will tell us what's going on. So this particular one, as an example, is just increasing in brightness. But it's a lot more useful than that. So here you have pulsating stars. So these are stars that physically change size, they pulsate, and they have a regular period. So if you were to do a light curve, you'd get something that varied with a regular pattern over time. And the good thing about these particular stars is that the period, the time it takes to go through one cycle, can relate to how bright the actual star is. So you can then calculate a distance to it. So we can calculate those sort of things. We know that it's pulsating purely by looking at the light curve and things like that. We can detect exoplanets. So when a planet passes in front of a star, it blocks out some of the light. So how long it takes place for, how much light it blocks out, can basically give you the size of the planet and also its orbit. So we can get a huge amount of information about the planet that we can't even see just purely by how it blocks out the light from that star. And then you have things like supernovas. I mean, there's lots and lots of different things you can study with a light curve, but supernovas, you'd have a sudden increase in its brightness, and then it would slowly dim down back as it kind of cooled down and expanded. If it's a type 1a supernova, they should always have a peak or the same peak brightness. So if you measure how bright you see it as, we know how bright it should be from a set distance. You can then work out a distance to it as well. And this is how we calculate some of the larger distances in our universe. So thank you for watching, and if you enjoy, then check out some of the other videos.